At the heart of nearly every large galaxy lies a cosmic behemoth, a force so powerful and mysterious that it defies our understanding. These are supermassive black holes, the enigmatic giants of the universe. Their masses can range from millions to billions of times that of our Sun, making them some of the most massive objects in existence. These cosmic giants exert an enormous influence on their surroundings, shaping the evolution of galaxies and the behavior of stars. They shape the very fabric of space and time around them, warping it in ways that challenge our understanding of physics. Imagine an object so dense that not even light can escape its grasp. That's a black hole, a region where gravity is so intense that it bends light and distorts reality. Now scale that up to the mass of millions of suns, and you begin to grasp the sheer magnitude of a supermassive black hole. You've got a supermassive black hole, a cosmic monster with an insatiable appetite for matter and energy. These cosmic monsters lurk at the centers of galaxies, influencing their structure and dynamics. Our own Milky Way harbors one such beast called Sagittarius A*, a supermassive black hole that lies at the very heart of our galaxy. It weighs in at about 4 million solar masses, a staggering amount of mass concentrated in a single point. But how do we know these giants exist? We can't see them directly. They're black after all, absorbing all light that comes near. Instead, we observe their effects on nearby matter, such as stars and gas clouds that orbit around them at incredible speeds. By studying the motion of these objects and the radiation emitted from the accretion disks of matter spiraling into the black hole, we gather indirect evidence of their presence and properties.
Supermassive black holes exert an immense gravitational pull on their surroundings. This force affects everything nearby, especially stars. Imagine a cosmic dance floor. The black hole is the central dancer. Stars are its partners, twirling around in elaborate orbits. The closer a star gets, the faster it must move to avoid falling in. It's like a celestial game of gravitational tug-of-war. Stars in this region move at incredible speeds. Some zip around at thousands of kilometers per second. These high-velocity stars provide crucial evidence for the existence of supermassive black holes. By studying their orbits, astronomers can calculate the mass of the central object. The black hole's gravity also affects star formation.
As matter falls towards a supermassive black hole, it forms a swirling disk around the black hole. This is called an accretion disk. Think of it like a cosmic whirlpool. Gas and dust spiral inwards, getting hotter and denser as they go. The accretion disk is far from a peaceful structure. It's a turbulent, violent place. As matter in the disk rubs against itself, it heats up. The inner regions can reach temperatures of millions of degrees. At these temperatures, the gas glows brightly. It emits light across the electromagnetic spectrum. From radio waves to X-rays, accretion disks are cosmic beacons. They're some of the brightest objects in the universe. Accretion disks are key to understanding black hole physics.
Quasars are among the brightest objects in the universe. They outshine entire galaxies. Quasars are powered by the intense activity around supermassive black holes. They're like cosmic lighthouses, visible across billions of light years. At the heart of a quasar is an actively feeding black hole. It's surrounded by a bright accretion disk. This disk can emit as much energy as trillions of suns. Quasars are so bright they can outshine their entire host galaxy. Quasars are just one type of active galactic nucleus, AGN. AGNs are galaxies with extremely bright centers. They're powered by actively feeding supermassive black holes. Studying quasars and AGNs helps us understand cosmic history.
Some supermassive black holes don't just pull matter in, they also shoot it out at incredible speeds. These are called jets. Imagine beams of particles and energy extending for thousands of light years. Jets can travel at nearly the speed of light. They're nature's most powerful particle accelerators. The process likely involves the black hole's magnetic field and rotation. As matter falls into the black hole, some of it gets accelerated and ejected along the magnetic field lines. These jets have a profound impact on their surroundings. They can extend far beyond their host galaxies. Jets can also trigger or suppress star formation. Studying these jets gives us insights into extreme physics.
Supermassive black holes don't just sit idly at galactic centers. They play an active role in shaping their host galaxies. This influence is known as feedback. The black hole's activity can affect star formation, gas distribution, and even the galaxy's overall structure. One way black holes shape galaxies is through their powerful outflows. As the black hole feeds, it can generate intense winds and jets. These can push gas out of the galaxy's central regions. This process, called quenching, can slow or stop star formation. There's a mysterious correlation between a galaxy's central black hole mass and its overall properties. Bigger galaxies tend to have bigger black holes. This suggests a co-evolution between black holes and their host galaxies. Understanding this relationship is a key area of current research.
Near a supermassive black hole, tidal forces become extreme. These forces are so intense that they can stretch and compress objects in ways that are unimaginable on Earth. These are the same forces that cause ocean tides on Earth, but on a much grander scale. The gravitational pull of the moon creates tides in our oceans, but near a black hole, the forces are magnified to an extraordinary degree. But near a black hole, they're amplified to cosmic proportions. The closer you get to the black hole, the stronger these forces become, reaching levels that can tear apart entire celestial bodies. Imagine a force so strong it can stretch and compress entire stars. These forces can elongate a star into a thin, elongated shape, almost like a piece of spaghetti. That's the power of a supermassive black hole's tidal forces. They are capable of distorting the very fabric of space and time, creating phenomena that are both awe-inspiring and terrifying. They create a cosmic tug-of-war that can tear apart anything that ventures too close. This tug-of-war is a battle between the gravitational pull of the black hole and the structural integrity of the object. These tidal forces arise from the difference in gravitational pull across an object. The side of the object closer to the black hole experiences a much stronger gravitational force than the side farther away. The side closer to the black hole feels a stronger pull than the far side. This difference in gravitational pull stretches the object, creating immense stress and strain. This difference increases dramatically as you get closer to the black hole. Near the event horizon, the point of no return, these forces become almost infinitely strong. At a certain point, called the Tidal Disruption radius, the force becomes strong enough to overcome an object's internal gravity. This is the point where the object can no longer hold itself together. For a star encountering a supermassive black hole, the results can be spectacular. The star is torn apart, its material stretched and compressed, creating a brilliant display of light and energy. This process, called spaghettification, is one of the most violent events in the universe. The star is stretched into a long, thin shape, and its material is eventually swallowed by the black hole, adding to its mass and energy.
Sometimes, a star wanders too close to a supermassive black hole, a cosmic giant lurking in the heart of a galaxy. What happens next is a cosmic cataclysm called a tidal disruption event, or TE, a phenomenon that dramatically alters the star's fate. The star gets stretched and shredded by the black hole's intense tidal forces, a process that can take mere hours or days. Part of the star's material gets flung away into space, creating streams of stellar debris that can travel vast distances. The rest of the material falls towards the black hole, igniting a bright flare of activity that can be observed across the universe. These events are rare but incredibly illuminating, offering a brief yet powerful light show. They give us a unique glimpse into the feeding habits of supermassive black holes, revealing how these cosmic giants consume matter. When a TDE occurs, the black hole's accretion rate suddenly spikes, dramatically increasing the amount of material it absorbs. This causes a bright flare that can outshine the entire host galaxy, making the black hole temporarily one of the brightest objects in the sky. Studying TDEs helps us understand the population of supermassive black holes in the universe, shedding light on their distribution and frequency. Each event gives us valuable information about the black hole's mass and spin, crucial data for astrophysicists. TDEs also provide a unique laboratory for studying extreme physics, allowing scientists to test theories under extreme conditions. Through simulations and computer models, researchers can predict the outcomes of TDEs, enhancing our understanding of these dramatic events. Observatories around the world capture these events, with telescopes monitoring the flares to gather as much data as possible. Future missions aim to study TDEs in greater detail, promising new advancements in our knowledge of black holes and their interactions with stars.
Studying supermassive black holes is a challenging task. After all, they're black. They don't emit light. So how do astronomers observe these cosmic giants? The key lies in studying their effects on surrounding matter. We use a variety of techniques and instruments to peer into the darkness. One crucial tool is X-ray astronomy. Accretion disks around black holes emit X-rays. These high-energy photons can penetrate cosmic dust and gas. They give us a clear view of the inner regions near the black hole. Radio astronomy also plays a crucial role. Many active galactic nuclei emit strongly in radio wavelengths. Optical and infrared observations are important too.
Supermassive black holes play a complex role in galactic star formation. On one hand, they can trigger the birth of new stars. Their gravity can compress gas clouds, causing them to collapse and form stars. On the other hand, they can also disrupt star formation through intense radiation and outflows.